So welcome to my talk about accelerated analog neuromorphic hardware. It is a short summary of the wafer-scale system and the future developments in this area we do in Heidelberg. Karl-Heinz already showed 2 days before the outline of the project and how it's embedded in the Human Brain Project, and I will now go a little bit more into the technical details. The motivation, I will make this short because we have heard it so many times, and I think it's the same here. It's that we want to learn about how the biological brain processes information, so we want to understand biological information processing, and which is more or less the other side of the same coin, we want to use it to build future computing devices. And for both things, we need models to test our ideas. And as far as I know, there are only 2 modeling possibilities at the time. You can build a numerical model, that means a computer simulation, or you can build a physical model, and that is what neuromorphic hardware or analog neuromorphic hardware is all about. And this physical model represents the model parameters as physical quantities. That means, as in nature, it's voltage, current, or charge. And we will see this later. You can combine both methods to form a so-called hybrid system. This is an example, the most simple example of a physical model. It is a basic model for the membrane of a biological cell. You can put this in a simple equation and model this equation by a simple electrical circuit. And here is, I think, the one key feature which sets our work apart from what we have seen so far is that we do not try to get the time constants in this model close to biology. We do, in contrary, we use the fact that the physical properties of the resistors, the capacitors, are different in VLSI compared to biology. And so if we put this all together, our time constants here are much smaller than in biology. We have higher currents, we have lower capacitances. And that leads, at the end, to a continuous time model for this kind of equations, a physical model, but at an accelerated time. So in our case, it can go up to 10 to the power of 6 times the speed of biology. But due to the problems with communication, we also use a little bit smaller acceleration factors. But our models are always accelerated, so they are not comparable to real-time systems. You should keep this in mind if you see the details of the system later. And now, if you build such a neuron, we can put it in a chip, and then you measure some activity. So here, this is just an example of a postsynaptic potential with a different number of synapses at different rates projecting on it. And you see this is an analog measurement. You have noise here on it. This is noise here from some feed-through from another signal. But you might want a little bit more complexity. So we used a little bit more complex model, the adaptive exponential integrated fire model, which also supports the second variable besides the charge on the membrane for some kind of adaptation. And then the circuit just becomes a little bit more complicated. We still have the capacitor here in the center, but now we have several conductances connected to this capacitance. And also we have to add some nonlinear things like a reset term and so on. A neuron this way then is layouted and put on the chip. This is just an example of the layout of this kind of adaptive exponential integrated fire neuron, just to show you that at the end, all these circuits add up to a lot of components. So this is 200 micrometers times 20 micrometers, and these are 2 neuron circuits. So I don't think you got the area right, sorry, in the last slide, because it's not what was on the slide in the previous talk. It's only this 200 square micrometers per neuron. And then this neuron can have much more complex firing modes because it has now two variables, so you can have simple tonic spiking. These are all measurements. You see the noise again. You can always see the measurements, also identify them by the noise. And it also supports adaptation. You see the spike rate changes, or bursting modes, or the combination of burst and adaptation, which gives you initial bursting and then tonic spiking, for example. These are all firing modes you can record from real neurons, and I think, we think it's necessary to be able to replicate them in this kind of physical model system. The next step is that you want to compare the behavior of this kind of neurons with the model, and to do this we have to resort to numerical simulations because it's the only way to prepare a reference here. This is a numerical simulator, and then we use our analog circuit and compare the response and try to calibrate the response to the model so that the user of the system gets the response from the neuron he expects. Sorry. Okay, so this is what the single neuron does. The next step is you want to have several neurons acting together. And here is a simple example. Here only the spike times plotted of now a network of neurons connected in a chain-like fashion. So these neurons here excite their neighbors, and so you get an excitation going through the network. This is now transferred to wall time. So in reality, this happens here in 1 millisecond, not in 1,000. It's a factor of 10,000, so 100 microseconds is the real time here. With this kind of networks now, you can also do more complex things. This is just an example of a simple attractor network. Here, the small external input switches the whole system between two attractor states. Or this is what Mihai showed yesterday. We can try to prepare a kind of a Boltzmann machine within this kind of network. So the neurons here learn to represent a certain distribution. We have seen this yesterday. So this was just a short overview of what you can do with this kind of neurons. Now let's go through all the aspects of modeling neurobiology to make such a model really useful to understand the biological system or to test ideas of the biological system. So we have to be able to capture the important aspects of the biological system. What I've shown so far is things about the neurons and neuron behavior. So in biology, we have a multitude of neuron morphologies and electrophysiologies, and we try to cope with this, that these neurons I've shown are heavily parameterized circuits. So we have a lot of parameter storages. We have 24 analog parameters for each of these neurons. But this needs a complicated calibration before you can start to perform experiments. We also, in Heidelberg, did I'm not going to show this, multi-compartment neurons, backpropagating action potentials, dendritic spikes, and gap junctions. This is all very easy in analog and can be cheaply implemented without increasing the power budget. That's what we are planning to do is to integrate these low NMDA plateau potentials and calcium spikes so that you can really build a realistic model of a pyramidal neuron as far as we understand this neuron today. A very difficult problem for our kind of modeling, and I'm not sure how you can ever put this in, are electrical synapses, because here you have then coupled equations and you cannot use a digital spike transport anymore. I have not seen, also in the last days, I have not seen any idea how to do this in neuromorphic hardware. Maybe this will still be the realm of numeric simulations for the foreseeable futures, because this is the end of digital spike transport. If you have electrical synapses, you really need an analog connection between all the neurons. So gap junctions is easy because this is only connections from one soma to another, but for electrical synapses you really have to have a network of analog connections, so this is very complicated to build and calibrate. Connectivity is another thing. We have heard a lot about connectivity in two talks before, and we do not aim for these numbers like we have seen, let's say, human size mouse size. I don't care about what, I mean, I have only neurons which model some equations. This has nothing to do with animals. So I can only count them, and they are large, and I don't get many. So I think there's still more than enough to do useful stuff and learn a lot about how to train neural networks to do things. But we would need approximately 2.5 million wafers to build, to reach the numbers of the human brain. So this is unfeasible. But our neurons are realistic from their fan-in and fan-out, so we can easily support 14,000 inputs per neuron. So we have already done this, so this is working. So you can build small networks which run very fast to test your ideas of how the training can work in this kind of assemblies. And I think small, if you look at the numbers, a few 100 million synapses is still a lot. And the problem is really that all these synapses need some values, need some set of parameters. So I'm not sure how the larger networks will be really trained in foreseeable futures. So I think at the moment this is enough for our purposes. This is how it looks like. If you put this all together, this is a 20 centimeter wafer. And what you have seen before was all recorded from this kind of circuit. So all the measurements were done with this kind of circuit. And if you look at the enlargements, you see that here the individual chips, this is the structure you see below, they are interconnected by this small structure. Here's an enlargement. These are small connections. They are put on top of the wafer later. We call it post-processing to interconnect the individual chips on the wafer. This is how an individual chip looks like. You can see where at the edge where the post-processing was not applied, you can see beneath the post-processing these small network chips. And each network chip has 500 neurons and 114,000 synapses. And these wafers then have to be mounted, and they are mounted in this kind of big system with an aluminum frame. And they need some cooling here. This is the back side of the wafer where we have some cooling. We have here, you can see it, a lot of FPGA boards to handle the communication. The reason why we need so many FPGA boards here is the acceleration factor. We have 10,000 times the data than a real-time system with the same number of neurons and synapses. So we need 10,000 times the bandwidth. And this means we need 50 Kintex FPGAs from Xilinx to cope with the data rates here. Each of them has, I think, 1 gigabyte of memory to record the spike traces and to send spikes mimicking external signals into the system. Spikes can also be sent through Ethernet into the system, so we can build a hybrid system where we have, for example, a retina running on the classical computer, sending spikes to the wafer. The wafer represents some parts of V1, for example, doing something with these spikes, and you can also send spikes back to the computer to change, for example, move the eye, the virtual eye, things like this. And these modules then end up here in our machine room at the moment. We will have 20 of these systems in operation, and there is this big opening of the platforms Karl-Heinz already told you about. And so visit the website if you want to get access to this system, then you can play around with these networks. Okay, so that's for scaling the size. But there are other very important aspects, and this is the topic of the second half of my talk. So one thing, we have continuous time operation in biology. This is also in our model. It's an analog continuous time model. And in the biology, we have time scales ranging from milliseconds to years. And here's the big advantage of the accelerated model, and maybe the main reason why we do this is that to catch the biological timescales of years, you have to have a fast system or you will stay in the lab forever. So the accelerated model compresses these time scales so that they are accessible in the laboratory, so to say. What we do not have, and also this is a big problem, I have not an easy solution for the future, only an approximate solution, is the controlled delays. You know all the axonal connections, if they are myelinated, they are very precisely controlled. There is plasticity in the delay in the brain, and this is very resource intensive to build this in an electronic circuit, so I'm not sure how this will enter the circuits in in the near future. But, and this is very important, plasticity, I think this is the main reason for the existence of this platform, to test learning, to develop algorithms for learning. In biology, we have several levels of plasticity. The system, the most important one, I think, which is also mostly neglected is that it grows from a single precursor cell, so that it's not there and then it trains synapses, but it grows, and during growth the network comes into existence. And this is something you can emulate in an accelerated system, because you have the time to really emulate development, and you can grow synapses by changing the topology. You can grow cells by changing the topology, but you need large amounts of memory. We already have some provisions for this, so in principle you can try development. And the most important thing is that the genome codes for complex and diverse plasticity rules. It is not that we have one rule and then it learns from the data. We have thousands of rules, very varying over the place of in the brain, and only if they all work together correctly, then the animal lives and does what it's supposed to do. So we need a very flexible synaptic plasticity model, and we call it a hybrid model, and this is something we are now implementing for the next generation of our systems, and I will show you a little bit about this soon. First, to the complexity. I was laughing because exactly the same slide was shown independently from me this morning, and this just shows the level of detail we know so far about synaptic plasticity and what's happening in the postsynaptic side here. This is only the postsynaptic side of the synapse. The presynaptic side is as complex and would give you as complex. There are a lot of publications. I just selected two summarizing this. So it is much more than a simple rule. And I must personally say, I don't think any device physics can catch this. This is absurd. So we will never have a single device doing this. Not a memristor, not a transistor, so we need more if we want to capture this. And I think without capturing this, we will never have anything like intelligence, because this is the basis of biological intelligence. This is where learning is coded. So we all, like everybody, man, this is too complex. So we started very simple. We have seen this also a few times. We started with spike time dependent plasticity, the famous measurements. I think we have seen the same data already. We tested this in a chip before the Wafer-scale. We built before the Wafer-scale system. This is also remotely accessible, so who is interested in doing STDP experiments in accelerated hardware can also contact us. And this works, you see the weight development here, and you see that from distribution it sharpens due to plasticity. I won't go into detail. So this is spike time dependent plasticity. And then the question is, if you have all this, how are you going from the idea to an experiment? And this is something to do with the number of parameters you have to fix. And in our case, we have a PyNN script, so it's a description of the experiment you are going to do in a derivative of the programming language Python. Maybe a few of you know this. So you describe your network, and then the software generates a lot of configuration information to configure all the routing and topology switches in the chip. And also, if you do not use plasticity, it has to calculate a weight for each synapse. So it's a tremendous amount of information you need. And here's where the problem comes in. Even if our system is not that large, as much smaller than the proposed systems from a lot of colleagues here, it still has, it already has millions of parameters, and they have to be selected and fixed for an experiment. So we have network topology, neuron size and parameters, synaptic strength. And at the current status is that everything has to be or is pre-computed on the host computer. And this is not really feasible in the long run, because it requires a precise calibration of the hardware so that what you calculate in the computer really does the same thing on the real hardware, and that's difficult for analog. Ich meine, Giacomo has some opinion to this. And it takes a long time because it's a lot of parameters, complicated floating point equations on a computer, so usually it takes much longer than running, much longer than running the experiment on the accelerated hardware system. So we have to do something more to solve this problem, and this was we called hardware hybrid plasticity. This is an enhanced way to do spike time dependent plasticity, which will give us, which will relieve us from the need to calibrate all the synapses. We will have plastic topology and also delays. Sorry, I just wanted to, okay. And what I call this that we want to really replace calibration with learning. So this is what we changed from the current system. So don't look at the details, but in basic you have an analog network core where your synapses are, and what we added are two kind of microprocessors called plasticity processing units. Here's a photograph of a prototype we also demoed 2 days ago. So we have synapse array, and here is the plasticity processor directly next to it, and the neurons are below. And this plasticity processor is a SIMD parallel processing unit. For each column of synapses, so you have in the final chip we will have 256. We will have an ADC, and then the digital value of the measured correlation in the synapse is sent to this processor. So for each synapse, you have a lot of circuits, but important is here that we have this correlation sensor and the weight. The weight projects to the neuron, the dendritic input, and produces a post-synaptic potential. And the correlation sensor measures the temporal difference between pre and post signal. But this signal is then stored in the synapse, sent through an ADC, because it's analog, to the digital plasticity processing unit, which then runs software calculating the update of the weight and sending the updated weight back. And the important thing is that the correlation measurement happens on a much shorter time scale than this update loop, because the correlation sensor has analog storage locally and can store the results for several correlations. Oh, man. So this was the signal that my time is over. But I've only two additional slides, so I think it's okay. And these are measurement results from this hybrid plasticity using a simple multiplicative STDP rule, the same we already had fully integrated in the previous chip, but now this measurement just shows that we can replicate with this hybrid scheme also the plasticity. Here's the time difference and the weight change. But, and this is the important thing, now we can have all shapes we want. So we can have symmetric ones, we can have asymmetric ones, we can have non-exponential ones. So the advantage of this processor is that it allows us to use arbitrary curves for update of the weights. And not only this, you can do much more. We have not yet tested this all, but you can include additional variables. You can use supervised plasticity, reinforcement learning. You can add, in principle, anything you can fit in the memory of this processor. And this is how we, together with the wafer-scale integration, this is how we want to proceed in the Human Brain Project with our hardware development, so that we really have a system which can train all these millions of synapses, even with complicated learning rules and non-standard learning rules, without external, without use an external host computer for this. So thank you.